couple of days ago, we gave you guys a new equation for electric field between parallel plates. E is equal to delta V over delta D. And we said when we introduced that equation, delta V stood for potential difference, which we said was related to the energy. It's not the energy, but it was related to the energy. Today we're going to learn a little bit more detail about that potential difference and what that potential difference really means. Okay? How is it related to energy? What's the relationship to energy? But first, before we do that, we're going to step backwards. In fact, step way backwards to physics 20 for just a few moments here. In physics 20, we defined work, or we defined, in one way at least, we defined work as the change in the gravitational potential energy. If I lift this pen up into the air and it gains 10 joules of gravitational potential energy, that must be because I did 10 joules of work on it, right? Work is equal to the change in energy. As the potential energy rises, I must have done work on it to give it that potential energy. In other words, W is equal to delta E. Easy enough, right? If it was easy enough in physics 20, it's easy enough now. It's the same thing. In the context of electricity, however, we would say not the work done in a gravitational field is equal to the change in gravitational potential energy, but rather the work done in an electric field is equal to the change in electric potential energy. So all you got to do in your mind here now is picture an electric field arrow instead of a gravitational field arrow. The work done against that gravitational field arrow is equal to the change in gravitational potential energy. The work done against an electric field arrow is equal to the electric potential energy change. If blue is gravity and red is electric, the work done when I move a mass through this gravitational field is equal to delta E. If this is a charge, the work done in moving this charge through this electric field is equal to delta E, the change in potential energy. In other words, it's the same thing, except that it's a different field, that's all. Now, we can also define electric potential energy in a bit of a different way. I'm going to cover that up for a second, actually, because I don't want you to write that quite yet. Gravitational potential energy, you guys learned in physics 20, is the energy due to an object's height. The height it is above the ground determines its gravitational potential energy. The higher it is, the more gravitational potential energy it has. The energy stored in an object due to its height above the surface. That's not truly correct. That's a good definition, by and large, for almost every situation that you would ever come across. But it's not, strictly speaking, a correct definition. It just works for almost everything we'll ever come across. Strictly speaking, the gravitational potential energy is not the energy stored in an object in this remote control that I'm holding right now due to its height above the Earth. Strictly speaking, it's the energy stored in the system of this remote control and the Earth. It's the system that contains the energy, not the remote control. The reason we usually just say it's the remote control is because the Earth is so massive, is so heavy, that it isn't going to go anywhere, right? Which has the potential to move? Well, really, it's the remote control, even though technically they both have the potential to move, right? As I drop this remote control, the remote control falls toward the Earth actually rises toward the remote control because of gravity. But it's such a minuscule amount, we don't usually pay any attention to that. We just say gravity potential energy is the energy stored in the remote control, not in the system of the remote control and the Earth. When we're dealing with charges, however, charges are a lot closer to each other in magnitude than the remote control and the Earth are in mass. So then we have to go back to our better definition, which is not the energy stored in the one thing as a result of a height, but rather the energy stored in the system. We're going to define electric potential energy beyond defining the change of potential energy as the work. We're going to define electric potential energy as the energy stored in the system of two charges a certain distance apart, which again really should be the definition for gravitational potential energy as well. The energy stored in a system of two masses a certain distance apart. But because the Earth is so heavy, and usually that's what we're talking about in the context of gravitational potential energy, we can drop the second object. Because it's not the second object, the Earth, isn't going to move anywhere. You got two charges, though. They're probably going to be pretty close to each other in terms of magnitude. The negative will fall towards the positive, but the positive will also fall towards the negative. It's the energy stored in the system of those two charges. Again, as opposed to the Earth, where here's the Earth, here's the remote control. The remote control will fall towards the Earth. And although the Earth does rise towards the remote control, it doesn't really, right? For all intents and purposes, it doesn't. The energy stored in the system of two charges a certain distance apart. Now, I'm going to give you an example here, which is likely the most straightforward, simplest example that you will ever see in physics, period. This is such a ridiculously simple question that I'm not even going to ask you to write down the answer to this. We'll do it as a group here. You want to write down the answer, you go ahead. Moving a small charge from one position to another in an electric field requires 3.2 times 10 to the negative 19 joules of work. How much potential energy will be gained by the charge? How do we define work? The change in potential energy. How much work was done? 3.2 times 10 to the minus 19. What's the change in potential energy? Don't make this harder than it has to be. Tom? 3.2 times 10 to the minus 19, right? If work is equal to delta E, and this is 3.2 times 10 to the minus 19, then this is 3.2 times 10 to the minus 19 as well. Done. Well, if they were only all that easy. The good news is you may see something like this on your diploma exam. The bad news is if you do, it'll probably be a part of a bigger question. So you may have to know this, remember this, that W is equal to delta E, but it won't be a question on its own. Not likely, at least, because that's pretty, I mean, that's a pretty basic question if that was a question on its own, right? So it might be part of a bigger question. Take a look at those two practice problems. Let me cover up the answers because, oh my goodness, I wouldn't want you to see what the answers are. I'll give you 30 seconds to do both of those combined. Okay, 30 seconds. Bo, you got an answer for number one? Wow. You're so smart. 1.6 times 10 to the minus 19 joules. Good. Work is equal to the change in energy. If the change in energy is 1.6 times 10 to the minus 19, then the work done is also 1.6 times 10 to the minus 19. What about 2? This one is a little bit tougher. And by a little bit, I mean a little bit tougher. Who's got the answer for number 2? Tom? It's also 1.60 times 10 to the minus 19. The work is equal to the change in energy. Well, my goodness, we have to do a calculation on this one. We have to subtract two numbers, the final energy minus the initial energy. And when we do that, we get 1.60 times 10 to the minus 19 joules. Easy enough. Now, we do some pretty complicated questions sometimes and some pretty tricky concepts sometimes. And when we do example problems, usually we take them from the book, although every once in a while I put my own example problem up there if I think I can do better. And often what we find is that there's one example for a particular concept. And sometimes it's like, well, geez, it'd be nice to have another example because this is a tough concept. This is perhaps the world's easiest concept. W is equal to delta E. But for whatever reason, in this particular concept, they give us 2 examples. Some of the hard ones, they gave us 1. And then for this one, for whatever reason, just in case you had trouble identifying that W is equal to delta E, here's another one to see if you can figure this one out. When a small positive charge moves from a negative plate to a positive plate, this much work is done. How much electric potential energy did it gain? What's the answer? Emma, what's the answer to that one? You guys are brilliant. 2.3 times 10 to the negative 19 joules. All right, if this is the work, then that's also equal to the change in energy or the potential energy gained. Okay, I'll give you another 30 seconds to answer. Oh, covered up. To answer that question. Oh, no, I'm not even going to give you 30 seconds for this one. 10 seconds. Caitlin, what's the answer to this one? Yes, good. 4.00 times 10 to the 5. If this much potential energy was gained, then the work done is going to be equal to 4.00 times 10 to the 5 joules. Is that okay, guys? I mean, this seems ridiculously easy, doesn't it? And you know what? It is. If you remember that definition. If you remember that work is delta E. If you don't, then this isn't easy. If you remember W is equal to delta E, then you can't make a mistake on this. But if you come across a question on a diploma exam that's a bigger question, maybe it's a page of information, and this is only one small part of that question, all of a sudden it becomes easier to make a mistake, right? To forget that definition when it's out of context, okay? We have to remember that the work done against an electric field is equal to the change in potential energy. If we do, we're good to go. Easy. If we don't, not so much. Okay, well, let's add one more term to this whole analysis of work and change in potential energy. We know from physics 20 that work is equal to F times D. Well, it is in physics 30 as well. But this time it would be not the gravitational force, it would be the electric force in this case. And the electric force would likely be found, if we needed to find it, by using the field equation Q times E. So to move a charge through a certain electric field, we need to do work on it. If we have the number for the amount of work done or the change in potential energy, that's great. But if we don't, if we have the charge in the electric field strength in the distance between the plates, then we can find the work done by using F times D or Q times E times D. Now, one more new term. This is close to one that we looked at last week. We talked about potential difference. Electric potential, again, is related to energy. But how is it related to energy? It's the amount of energy per coulomb. So let's use an analogy here. There's 13 of us in this room right now. Let's say we have $65 total. If energy is money, then the total energy we have is 65. The money per person would be what? Okay, just stop writing for a second, Akira, and just think about what I just said. Money is energy. We have 13 people in this room right now. The total amount of energy we have, or the total amount of money we have, is $65, 65 joules. How much money per person, or how much energy per person do we have on average? How do you figure that out? 5, right? So 65 would be the energy, 5 would be the potential. the energy per person or the energy per coulomb of charge. Does that make sense? We talked about potential difference. We said it was related to the energy, but not exactly energy. It's not exactly energy because it's the energy per coulomb of charge as opposed to a total amount of energy. Here's a symbol for potential. Not quite the same as potential difference. You'll see the difference in just a moment too. Potential is energy per charge. It's like saying Simon did this in his head. He divided 65 by 5, right? Or sorry, 65 by 13. The amount of money divided by the number of people. Okay, the amount of energy divided by the amount of charge gives you the total amount of energy per charge. And the units for that, of course, would be either joules per coulomb or volts. Final new slide. We talked about potential, the energy per charge. Potential difference is the difference in energy per charge. So the difference in potential between two spots, right? Potential difference is going to be the difference in potential. We can find that by subtracting the final minus the initial. You want to find a difference in anything, it's final minus initial, right? If we use our analogy again, $65, 65 joules, or 5 joules per person, $5 per person. Well, the potential difference, if I went to 7-Eleven and bought a Slurpee, the potential difference, if we all went to 7-Eleven, might be 2. Right? We all went to 7-Eleven with $5. We all came back from 7-Eleven with $3. The potential difference was $2. We all spent $2. The difference in potential between two spots. The final minus the initial, $3 minus $5. But we could also find it by saying delta E over Q. If 13 of us went down to 7-Eleven, each bought a Slurpee, then we would have spent $26. The change in potential energy was 26. Divided by 13 of us gives me 2. So I can look at it as I started with $5. We all started with $5. We all ended with $3. We all had a potential difference of $2. Or we can look at it as total, we lost $26. And there's 13 of us. We still have a potential difference of 2. So either way you look at it, we end up with the same number there. You don't need to write this down if you don't want to, what I'm about to do right now, but pay attention because it's good mental exercise there. This is what kind of brings us around full circle. Work is equal to F times D, right? We established that a few minutes ago. We established that in physics 20, even in science 10 actually, that W is equal to F times D. But in the context of electricity, we established this a few minutes ago. The force would be the electric force, and that would be Q times E, right? E is equal to delta V over, F over Q. Rearrange it to solve for F, it's Q times E. So we're going to replace F with Q times E. But we know the electric field is also equal to delta V over delta D. Or in other words, delta V is equal to E times D. Take a look at this. E times D. So now it becomes W is equal to Q times delta V. The work done against electric field is equal to Q times delta V. Well, what's Q times delta V? Let's rearrange this equation. Delta E is equal to Q times delta V. Didn't we start off this lesson by saying W was equal to delta E, the most basic physics problem that we'll ever see in physics 30, W is equal to delta E. One quick term here, guys, and then that's it for us. This is a new unit of energy. When you look at your power bill at home, energy is measured in kilowatt hours. That's not a joule. In fact, that's 3.6 million joules. But energy can also be measured in joules. Energy can also be measured in kilojoules or calories. There's all kinds of units that we can measure energy in. Just like there's all kinds of units that we can measure speed in, meters per second, kilometers per hour, miles per hour, and so on. Different units are convenient at different times. When you're traveling on the highway, it's convenient to measure speed in kilometers per hour. When a snail is crawling along the ground, it's convenient to measure speed maybe in centimeters per hour. When you're measuring energy in a can of Coke, it's convenient to measure energy in calories. It's actually kilocalories, not calories. They just say it's calories. Sometimes you see it measured in kilojoules. When you're measuring energy that you consume in your house, electricity, it's convenient to measure it in kilowatt hours. Sometimes it's convenient to measure energy in this new unit of energy that we call an electron volt. An electron volt is defined as the energy that's gained or lost by an electron as it moves through a potential difference of 1 volt, which ultimately, if we take a look at that energy, E is equal to Q times delta V, which is this equation right here, 1.6 times 10 to the minus 19 times the potential difference of 1 volt. It means that an electron volt is equivalent to a really small amount of energy, 1.6 times 10 to the minus 19 joules. Just like a kilowatt hour is equivalent to a really big amount of energy, 3.6 million joules. So when you're measuring a lot of energy, like you are when you measure the amount of energy that you consume electrically in your house, we want a big unit, kilowatt hours. When we're talking about the energy gained by an electron, we probably want a small unit, maybe an electron volt, 10 to the minus 19 joules. Here's one example for us. 565, it says, moving a small charge of 1.6 times 10 to the minus 19 coulombs between two parallel plates increases its potential energy by 3.2 times 10 to the minus 16 joules. What's the potential difference between the two plates? Here's the charge. What's this? What's this? Yes? Good. It's delta E, not E. It's not energy. It's change in potential energy. So we could call this delta E, or we could call it W, either one, because they both mean the same thing. We're looking for not V, that's potential. We're looking for delta V, the potential difference, the difference in energy per charge between two spots. We want to find the value of that potential difference. Well, we have two equations to describe that. There's VF minus VI. That doesn't look very helpful to me right now. But there's also delta E over Q. 3.2 times 10 to the minus 16 divided by 1.6 times 10 to the minus 19 gives me 2.0 times 10 to the 3. And the units would be either joules per coulomb, or you could say 2.0 times 10 to the 3. What other units could we use there? Last thing I'm going to ask you to tell me today. Volts. Good. Either one of those is just fine. Here's what you're going to do for the next couple minutes. You're going to finish these up in class here so that you have no physics homework tonight whatsoever. Except for a little quiz, that is, on charge distribution. Okay? So questions 1 and 2 on page 65, plus a little charge distribution quiz. But it should be, if what we did earlier today and yesterday makes sense, then you should be absolutely fine for that question as well. All right, that's it for today.